Welcome to the story. In this video, we explore how engineering began long before machines, formulas, or modern science. We'll trace the origins of human problem-solving, from survival and shelter to the first steps toward civilization. This is the story of engineering before it had a name. Long before the word engineering existed, long before drawings, calculations, or written knowledge, humans were already solving problems, adapting to their environment, and shaping the world around them in ways that would later define the foundations of engineering itself. In those early times, survival was not guided by theory or formal understanding, but by instinct, observation, and a deep connection with nature, where every decision carried consequences and every small improvement could mean the difference between life and death. Early humans lived in a world that was unpredictable and often hostile, surrounded by changing climates, wild animals, limited food sources, and landscapes that offered both opportunity and danger, forcing them to constantly adapt, experiment, and learn through experience rather than instruction. Without knowing it, they were already thinking like engineers, identifying problems such as exposure to cold, lack of shelter, or the difficulty of transporting food and resources, and then slowly developing solutions using the materials and knowledge available to them at the time. A fallen tree could become a protective barrier. A cave could transform into a shelter, and stones shaped by hand could serve as tools, weapons, or building elements, all emerging from repeated trial and error rather than deliberate design. These early innovations were not planned in advance, but discovered gradually, refined over generations, and passed down through observation and imitation, forming the earliest form of technical knowledge long before writing or formal education existed. Fire, for example, was not simply a source of warmth or light, but a technological breakthrough that changed how humans interacted with their environment, allowing them to cook food, harden tools, protect themselves, and extend their activities beyond daylight hours, effectively reshaping daily life and social behavior. Similarly, the ability to select stronger stones, bend wood without breaking it, or position shelters in protected areas showed an intuitive understanding of materials, forces, and environmental conditions, even if those concepts had no names yet. What makes this period remarkable is not the complexity of the solutions, but the mindset behind them, a mindset driven by necessity, curiosity, and adaptation, where each improvement was built upon previous experiences, slowly forming a chain of knowledge that would grow stronger with time. Engineering, in its earliest form, was not about precision or optimization, but about survival, resilience, and the human ability to observe patterns, learn from failure, and apply simple ideas in practical ways. This silent, almost invisible phase of engineering laid the groundwork for everything that followed, because before humans could design structures, machines, or systems, they first had to learn how to think in terms of cause and effect, materials and limitations, problems and solutions, setting the stage for the long journey from instinctive survival to intentional creation. As human populations slowly grew and began to settle for longer periods in the same areas, daily life started to revolve less around constant movement and more around stability, cooperation, and the careful management of resources, which naturally led to new challenges that required more deliberate and structured solutions. Survival was no longer just about reacting to immediate danger, but about anticipating needs, protecting groups, and creating environments where life could be sustained over time rather than from one day to the next. Food, water, and protection became central concerns, shaping how early communities chose their locations and organized their activities, with rivers, fertile land, and natural shelters playing a critical role in determining where people lived and how long they could remain there. The need to store food, prepare meals, and protect supplies from animals and weather pushed humans to create more reliable shelters, gradually evolving from temporary protection into more permanent structures that reflected an understanding of space, function, and durability. As families and small groups began to live closer together, social organization emerged alongside physical construction, requiring shared spaces, defined paths, and clear boundaries, all of which influenced how early settlements were laid out. Simple dwellings arranged around communal areas allowed for cooperation, communication, and collective defense, while the placement of shelters considered wind direction, sunlight, and proximity to water, revealing an intuitive awareness of environmental forces long before they were scientifically explained. Materials were chosen not for aesthetic reasons, but for availability and performance, with wood, stone, mud, animal hides, and plant fibers becoming the building blocks of early human life, each selected based on how well it could insulate, protect, or endure. Over time, people learned which materials lasted longer, which combinations worked best, and how to repair or reinforce their structures, transforming construction into a shared skill passed from one generation to the next. Daily routines also influenced early design choices, as spaces needed to accommodate sleeping, cooking, tool-making, and social interaction, forcing humans to think about organization, efficiency, and comfort in subtle but meaningful ways. Even the division between interior and exterior spaces reflected a growing awareness of privacy, safety, and climate control, marking an important shift from pure survival toward a more structured way of living. In meeting these fundamental needs, early humans unknowingly laid the foundations of engineering thinking, where observation, adaptation, and repetition created systems that improved life incrementally, proving that engineering did not begin with grand inventions, but with small, thoughtful responses to everyday challenges that shaped how humans lived together and interacted with their environment. As early human groups became more confident in their ability to secure food, build shelter, and protect themselves from immediate threats, temporary camps slowly began to transform into more stable settlements, marking a significant shift in how humans related to both space and time. Life was no longer defined solely by short-term survival, but by continuity, memory, and the gradual accumulation of shared experience, allowing people to remain in one place long enough to observe patterns, improve structures, and plan for the future. These early villages were not designed according to formal plans, yet their layouts reflected a growing sense of order and purpose, shaped by daily movement, social interaction, and environmental constraints. Homes were often clustered together for warmth and protection, while shared areas emerged naturally in the spaces between them, serving as places for food preparation, storytelling, tool-making, and decision-making, reinforcing the idea that built environments could influence social behavior as much as they responded to it. The permanence of these settlements encouraged experimentation, as structures could now be repaired, expanded, or rebuilt rather than abandoned, giving rise to better construction techniques and a deeper understanding of materials. Walls became thicker, roofs more stable, and foundations more deliberate, as people learned how weight, moisture, and weather affected their dwellings over time, gradually turning intuition into practical knowledge grounded in experience. With longer-term living came the need for infrastructure, even in its simplest forms, including pathways worn into the ground by repeated use, storage spaces for tools and food, and basic systems for managing waste and water. These early solutions were modest, but they represented a crucial step toward organized living, as humans began to shape their environment intentionally to support daily life rather than merely adapting to it. Villages also became centers of cultural and technological exchange, where ideas spread more easily, skills were refined, and roles began to specialize, allowing some individuals to focus on building, crafting, or problem-solving more than others. This gradual division of labor accelerated innovation, as knowledge accumulated and improved within the community, strengthening the foundations of what would later become engineering, architecture, and urban planning. The transition from camps to villages was not sudden or uniform, but it marked a turning point in human history, where built environments evolved from temporary solutions into lasting frameworks for living, reflecting humanity's growing ability to plan, cooperate, and create spaces that supported not just survival, but the beginnings of organized society. As early villages became more established, access to water and essential natural resources began to shape human settlements in deeper and more deliberate ways, influencing not only where people lived, but how their communities functioned and evolved over time. Rivers, lakes, springs, and coastlines were no longer simply convenient locations, but lifelines that supported agriculture, transportation, and trade, gradually becoming the structural backbone around which early societies were organized. Water provided more than nourishment, as it enabled irrigation, improved food production, and reduced the uncertainty of seasonal scarcity, allowing communities to grow beyond subsistence living. With this growing dependence came the need to manage and protect water sources, leading to the earliest forms of engineered solutions such as simple canals, channels carved into the ground, and barriers designed to control flooding or direct water toward fields and storage areas. These systems were often modest, but they required coordination, maintenance, and collective responsibility, reinforcing the connection between engineering and social organization. The availability of resources such as fertile soil, stone, clay, wood, and metals further influenced how settlements expanded and specialized, with construction techniques adapting to local conditions and materials. Stone-rich regions encouraged more durable structures, while areas abundant in timber developed wooden frameworks, each approach reflecting a growing awareness of material properties and long-term performance. Over time, this regional diversity in building methods laid the groundwork for distinct architectural traditions shaped by environment rather than aesthetics alone. Proximity to resources also transformed early economies, as surplus production enabled trade between communities, spreading ideas, techniques, and technologies across wider territories. Paths and routes connecting resource-rich areas emerged organically, forming the earliest transportation networks that supported exchange and communication, and further integrating engineering solutions into daily life. Living close to water also introduced new challenges, including erosion, flooding, and the need for sanitation, pushing early humans to develop adaptive strategies that balanced opportunity with risk. Elevated structures, reinforced banks, and carefully chosen settlement locations demonstrated an evolving understanding of natural forces, where observation and experience guided construction decisions long before scientific measurement was possible. Through their relationship with water and resources, early societies learned that engineering was not just about building structures, but about managing systems, anticipating change, and creating sustainable solutions that supported growing populations. These lessons would echo throughout history, shaping civilizations and influencing how humans continued to design environments that worked in harmony with nature rather than in opposition to it. As early civilizations began to emerge along fertile rivers and trade routes, human construction entered a new phase defined by order, geometry, and an increasing desire to understand and control space in a more systematic way. Societies such as those in Mesopotamia, Egypt, the Indus Valley, and later the ancient Mediterranean world developed not only more complex settlements, but also shared rules, measurements, and building principles that transformed construction from an intuitive craft into a disciplined practice guided by logic and repetition. For the first time, architecture and engineering became closely tied to mathematics and geometry, as builders relied on proportions, symmetry, and standardized units to achieve consistency and stability in their structures. Straight lines, right angles, and carefully measured dimensions allowed cities to expand in organized patterns, while monumental buildings reflected a growing confidence in humanity's ability to impose order on the natural world. Streets were aligned, walls were reinforced, and public spaces were designed with intention, reinforcing the idea that built environments could shape both movement and behavior. In ancient Egypt, architecture became a powerful expression of permanence and cosmic order, where massive stone structures were designed not just to stand, but to endure for eternity, aligned with celestial cycles and constructed with remarkable precision. These achievements required advanced planning, material management, and workforce coordination, revealing an early form of large-scale engineering that balanced symbolism with structural logic. Meanwhile, in the Greek world, a new emphasis emerged on human scale and visual harmony, where temples and public buildings were designed according to strict proportional systems that balanced beauty with structural clarity. Columns, entablatures, and carefully calculated spacing reflected a belief that architecture should mirror natural order, blending aesthetics with rational design in a way that deeply influenced future generations. The Romans would later expand on these principles, transforming geometry and order into practical tools for empire building, developing roads, aqueducts, bridges, and public buildings that prioritized durability, efficiency, and connectivity. Their innovations in materials, particularly concrete, allowed for larger spans and more flexible forms, enabling engineering solutions that supported growing populations and vast territories. Through the rise of early civilizations, engineering evolved into a shared language of rules, measurements, and methods, where knowledge could be taught, repeated, and improved across time. This shift marked a crucial moment in human history, as construction became not only an act of survival or belief, but a disciplined pursuit of order, balance, and long-term vision. As early civilizations began to emerge along fertile rivers and trade routes, human construction entered a new phase defined by order, geometry, and an increasing desire to understand and control space in a more systematic way. Societies such as those in Mesopotamia, Egypt, the Indus Valley, and later the ancient Mediterranean world developed not only more complex settlements, but also shared rules, measurements, and building principles that transformed construction from an intuitive craft into a disciplined practice guided by logic and repetition. For the first time, architecture and engineering became closely tied to mathematics and geometry, as builders relied on proportions, symmetry, and standardized units to achieve consistency and stability in their structures. Straight lines, right angles, and carefully measured dimensions allowed cities to expand in organized patterns, while monumental buildings reflected a growing confidence in humanity's ability to impose order on the natural world. Streets were aligned, walls were reinforced, and public spaces were designed with intention, reinforcing the idea that built environments could shape both movement and behavior. In ancient Egypt, architecture became a powerful expression of permanence and cosmic order, where massive stone structures were designed not just to stand, but to endure for eternity, aligned with celestial cycles and constructed with remarkable precision. These achievements required advanced planning, material management, and workforce coordination, revealing an early form of large-scale engineering that balanced symbolism with structural logic. Meanwhile, in the Greek world, a new emphasis emerged on human scale and visual harmony, where temples and public buildings were designed according to strict proportional systems that balanced beauty with structural clarity. Columns, entablatures, and carefully calculated spacing reflected a belief that architecture should mirror natural order, blending aesthetics with rational design in a way that deeply influenced future generations. The Romans would later expand on these principles, transforming geometry and order into practical tools for empire building, developing roads, aqueducts, bridges, and public buildings that prioritized durability, efficiency, and connectivity. Their innovations in materials, particularly concrete, allowed for larger spans and more flexible forms, enabling engineering solutions that supported growing populations and vast territories. Through the rise of early civilizations, engineering evolved into a shared language of rules, measurements, and methods, where knowledge could be taught, repeated, and improved across time. This shift marked a crucial moment in human history, as construction became not only an act of survival or belief, but a disciplined pursuit of order, balance, and long-term vision. As the classical world gradually declined and new social, political, and religious structures emerged across Europe, architecture and engineering entered a period of transformation driven less by imperial order and more by spiritual aspiration, local knowledge, and gradual innovation. The medieval era did not abandon the principles of earlier civilizations, but adapted them to new realities, where cities grew organically, resources were localized, and construction techniques evolved through craftsmanship rather than centralized planning. Medieval settlements were shaped by defense, faith, and community, with walls, towers, and fortifications defining the edges of cities, while narrow streets and irregular layouts reflected centuries of adaptation rather than predetermined design. Castles and fortified structures demonstrated an advanced understanding of load distribution, material strength, and strategic positioning, as builders learned how to use stone, mortar, and geometry to create structures capable of withstanding both time and conflict. At the same time, religious architecture began to redefine the relationship between structure and light, most notably through the rise of Romanesque and later Gothic cathedrals, where engineering innovations served a deeply symbolic purpose. Thick walls and rounded arches gradually gave way to pointed arches, ribbed vaults, and flying buttresses, allowing buildings to rise higher while becoming lighter and more open, transforming massive stone structures into soaring spaces filled with light. These advancements were not the result of theoretical calculations, but of accumulated experience, experimentation, and collaboration between master builders, craftsmen, and communities, where knowledge was passed down through practice rather than written formulae. Each cathedral became a living laboratory, refined over decades or even centuries, as builders adjusted proportions, materials, and techniques in response to structural challenges and aesthetic goals. Light itself became a central design element, as stained glass windows filtered sunlight into vibrant colors, reinforcing the idea that architecture could shape emotional and spiritual experience through engineering solutions. Height and verticality drew the eye upward, symbolizing a connection between the earthly and the divine, while structural systems worked quietly behind the scenes to support these ambitious forms. The medieval period demonstrated that engineering could evolve without formal science, relying instead on intuition refined by tradition, where innovation emerged through necessity and devotion. In pushing the limits of height, light, and structural complexity, medieval builders expanded the possibilities of construction, laying the groundwork for the rediscovery of classical knowledge and the human-centered thinking that would define the next great transformation in architectural history. As Europe gradually emerged from the medieval period, a renewed interest in classical knowledge, science, and the individual transformed the way humans understood space, proportion, and the purpose of architecture itself. The Renaissance marked a deliberate shift away from purely spiritual symbolism toward a worldview that placed human experience, perception, and reason at the center of design, reconnecting engineering and architecture with mathematics, anatomy, and the study of nature. Builders and thinkers of this era began to rediscover and reinterpret the principles of ancient Greece and Rome, studying symmetry, proportion, and geometry not as abstract concepts, but as tools to create spaces that felt balanced, harmonious, and intuitive to the human body. Architecture was no longer meant to overwhelm through height alone, but to relate to human scale, guiding movement, framing views, and creating environments that felt both rational and welcoming. This renewed focus on proportion led to carefully measured layouts, modular systems, and clearly defined relationships between structural elements, where columns, arches, and domes followed mathematical ratios that reflected a belief in universal order. Engineering during the Renaissance became increasingly analytical, as builders combined empirical observation with theoretical understanding, bridging the gap between craft and science in ways that had not been seen before. Advancements in drawing, perspective, and documentation allowed ideas to be shared more widely, transforming construction knowledge from localized tradition into something that could be studied, refined, and replicated. Architects and engineers began to design buildings on paper before they were built, testing proportions and structures through sketches and models, reducing uncertainty and increasing precision in execution. Urban spaces also evolved during this period, as plazas, streets, and public buildings were designed to encourage interaction, visibility, and civic identity, reflecting a growing belief that architecture could shape social life and cultural expression. Engineering solutions supported this vision through improved construction techniques, stronger materials, and a clearer understanding of load distribution and structural behavior. The Renaissance represented a turning point where engineering and architecture became conscious disciplines, guided by intention rather than tradition alone. By grounding design in human scale, mathematical clarity, and observational science, this era redefined the relationship between people and the built environment, setting the stage for the technological transformations that would soon reshape cities, industries, and societies on an unprecedented scale. As the world entered the Industrial Revolution, engineering and architecture underwent one of the most profound transformations in human history, driven by the rise of machines, new materials, and a fundamental shift in how work, production, and cities were organized. What had once been crafted by hand and guided by tradition was increasingly shaped by mechanical power, standardized processes, and the growing influence of industrial efficiency. The introduction of steam power and mechanized production changed not only how goods were made, but how buildings and infrastructure were conceived, as factories, railways, bridges, and warehouses emerged as dominant features of the landscape. These new structures prioritized function, speed, and scale, often sacrificing ornamentation in favor of structural clarity and economic performance, reflecting a world where engineering solutions were driven by productivity and expansion. New materials such as iron and later steel revolutionized construction, allowing for longer spans, taller buildings, and lighter structural systems that were impossible with stone or wood alone. Engineers began to think in terms of forces, loads, and efficiency, applying scientific principles to design structures that could support unprecedented weight and complexity. Bridges crossed wider rivers, trains connected distant cities, and industrial buildings reshaped urban environments with their vast interiors and repetitive frameworks. Cities expanded rapidly during this period, as populations moved toward industrial centers in search of work, creating urgent demands for housing, transportation, and public infrastructure. Engineering became inseparable from social change, as solutions were needed not only to build faster and larger, but to address sanitation, safety, and the challenges of dense urban living. Systems for water supply, sewage, and transportation reflected an evolving understanding of cities as interconnected machines rather than collections of isolated structures. At the same time, the Industrial Revolution introduced tensions between human scale and mechanical efficiency, as environments designed for production often overlooked comfort, health, and quality of life. This imbalance would later inspire new movements that sought to reconcile technology with human needs, pushing engineering to consider not only what was possible, but what was responsible. The age of machines redefined engineering as a profession rooted in science, calculation, and industrial logic, accelerating innovation at a pace never seen before. While it transformed landscapes and societies, it also set the stage for modern architecture, advanced materials, and the ongoing search for balance between technological power and human-centered design. As the modern era unfolded, engineering and architecture continued to evolve alongside rapid technological advancement, shifting once again in focus from pure industrial efficiency toward adaptability, sustainability, and the integration of human experience within increasingly complex systems. Steel, reinforced concrete, glass, and advanced composites allowed designers to explore new forms, heights, and spatial possibilities, transforming skylines and redefining what cities could become. Modern engineering embraced abstraction and innovation, moving beyond traditional constraints and experimenting with minimalism, modularity, and expressive structures that reflected both technological confidence and cultural identity. Buildings were no longer defined solely by their load-bearing walls, but by flexible frameworks that allowed interior spaces to change, adapt, and respond to evolving needs. Engineering became a tool not just for construction, but for expression, communication, and problem-solving at scale. At the same time, advances in computation and digital design transformed how structures were conceived, analyzed, and built, enabling engineers to simulate forces, optimize materials, and predict performance with remarkable precision. These tools allowed for more efficient use of resources, reducing waste while improving safety and longevity, marking a shift toward smarter, data-driven design processes that blended creativity with scientific rigor. As awareness of environmental impact grew, modern engineering faced new responsibilities, pushing sustainability to the forefront of design thinking. Energy efficiency, renewable materials, and climate-responsive architecture became central concerns, encouraging solutions that worked with natural systems rather than against them. Buildings began to harvest sunlight, manage water, and regulate temperature intelligently, reflecting a deeper understanding of long-term ecological balance. Looking toward the future, engineering continues to expand beyond physical structures into systems that connect cities, technologies, and people, including smart infrastructure, space exploration, and adaptive environments shaped by artificial intelligence and automation. Yet, despite these advancements, the core principles remain deeply human, rooted in the same instincts that guided early builders: observation, adaptation, and the desire to improve life through thoughtful creation. From simple shelters to complex global systems, the story of engineering is ultimately a story of human ingenuity, resilience, and imagination, reminding us that every structure, no matter how advanced, carries within it the legacy of those first problem solvers who shaped the world with curiosity, patience, and purpose. As we reach the end of this journey, it becomes clear that engineering is not just a collection of inventions, machines, or structures, but a quiet, continuous dialogue between human needs and the world around us. From the first shelters built for survival to the complex systems that shape modern cities and technologies, every step reflects the same desire to understand, adapt, and create something better than before. What connects early humans shaping stone tools to modern engineers designing sustainable cities is not technology itself, but curiosity, patience, and the willingness to learn from both success and failure. Engineering has always been about solving problems thoughtfully, responding to change, and finding balance between possibility and responsibility. As the future unfolds, new materials, digital tools, and intelligent systems will continue to reshape how we build and live. Yet the essence of engineering will remain deeply human, rooted in observation, creativity, and care for the environments we create. Each structure, each system, and each innovation carries traces of this long story, reminding us that progress is not a sudden leap, but a slow accumulation of knowledge over time. Thank you for spending this moment exploring the evolution of engineering. If this story helped you relax, reflect, or see the built world a little differently, feel free to stay with the channel, where many more calm journeys through science, design, and human ingenuity await.